Assalamu alaikum and very good afternoon to all of you. Today we are going to proceed with the computer architectures lectures. Today is the third week. However, today's lecture will be regarding the design half adder and full adder, and we have tomorrow lecture 1 hour. So tomorrow lecture I'm going to take the example of for addition and subtraction, and we'll go quickly through zero logic, and the rest we are going to complete it tomorrow. However, I am going to continue to what last lecture talked about design ALU, arithmetic logic unit. So as an important part of designing ALU is designing half adder and full adder. Now first of all, I'm going to start with design half adder. Okay, so design half adder, actually if you do summation for two number here, let we say two bit number, we have x and y. So here x, y. So you know the bits is 0001 and 10, that's for 2, 11, that's for 3. Now if you do addition between bit x and bit y, so this is, you will have sum and sometimes you have carry out, C out. So if I add 0 plus 0, what is the summation of 0 plus 0? Add them. 0 plus 0 is 0. There is carry out? No. So the carry out is 0. If I add 0 plus 1, so 0 plus 1, the summation is 1. The result is 1. There is carry out? No. The carry out is 0. 1 plus 0, so it will be summation is 1, but there is no carry out, 0. 1 plus 1, that's binary. 1 plus 1 is 2. That means the result is 0 and there is carry out is 1. Now that's the truth table for half adder. Now let's we get the truth table and present it in Boolean numbers. If you find out this is 0, if you find the sum, if we come to the sum, so what we have? We have 0, 1, 1, 0. Look to the sum table, sum column. If you just compare, if x 0, y 0, the result is 0. If x1, y1, the results also 0. Now if x is 0 and y1, or x1, y0, so if it's difference, see here, so if the numbers, the bit number for x similar to bit number of y, so the results of sum is 0. So here is 0, 0 and 1, 1, the result is 0. Why? Because it's similar. Now if the results are, if the bit number for x and y are variables, see here 0, 1 or 1, 0, the result is 1. And that comes to conclusion, if it's similar number for x and y, so the result is 0. Okay, if the similar if difference number of x and y, that comes to the results of 1. And thus make us reach to the conclusion. If you look to XOR truth table, if you have XOR truth table, XOR truth table give you, if you have similar number, see here similar number, if A0, this is XOR truth table. Just to remind you, I think you studied in year number 1, logic design. So if you see here A and B, both of them are 0 or both of them are 1, the result is 0. If A and B are variable, so one of them is 0 and one of them 1, or versa, one of the other one is 1 and the last one is 0, so the result is 1. So this is the truth table of XOR gate. So this is comes that sum equal to x XOR y. That's for this one. Okay. Now if we comes to C out, the carry, you find that if x, so the carry out will be only 1 only when x and y is 1. I think this is, it will remind you of the with the gate. Do you remember? If you come to the Boolean truth table for the gates, which gates does it remind you? Excellent. This is AND gate. So if you come back to the Boolean truth table for AND gate, you find it. AND gate, it will be the results 1 only when X and Y is 1. This is opposite for OR gate. You remember? OR gate, it will be 0 when X and Y is 1. And 1 in all the other cases. So this is different than opposite for OR gate. You remember that? Excellent. So this is remind you about AND gate. So if you come to Cout it will be X and Y. Now this one we could draw it like that. We could say that X, Y, if it's X and Y AND gate, so X and Y AND gate, so this is give you carry. If X and Y XOR gate, both of them goes to XOR gate, so this is give you summation, sum. So that's how we translate the truth table for half adder. Okay, we translate it to gates, and thus you find it inside the ALU design. Okay, thus if you have 1 bit, so 1 bit and 1 bit, so if you add 1 bit to 1 bit. However, if you add 3 bits, okay, if you have from hexadecimal 3 bits, so what you have, so that's for full adder design. We come to full adder design. Now how to design a full adder? So we have here 3 bit X and Y. Okay, so if it's 0 0 X and Y and Cn, the third input is Cn. So then what we have, same like what when designed half adder, we put Cout and sum. Okay, Cout, sum is the summation, and Cout is the carry out. Cout is the carry out. So we are going to follow same. So 0 plus 0 plus 0, result is 0, and there is no carry out. 0. 0 plus 0 plus 1, so the result is 1, and there is no carry out. 0 plus 1 plus 0, so the result is 1, and there is no carry out. 0 plus 1 plus 1, the result is 2. So the result 0 plus 1 plus 1, it should be result is 0 and carry out 1. That's 2 in binary number, you remember? So 2 you present it as a 0, and there is carry out is 1. Okay, so that's for this one. Then 1 plus 0 plus 0, so the result is 1, and there is no carry out, 0. Okay, 1 plus 0 plus 1, so this is binary, this is 2 in binary present as 0, and carry out is 1. Now it comes to other one. 1 plus 1 plus 0. 1 plus 1 is 2, plus 0 is 0, plus 2 is 2, plus 0. So 2 is 0 and carry out 1. 1 plus 1 plus 1 is a 3. 3 in binary is 1, and there is carry out is 1. So that's how we do the truth table in for full adder, for summation and for carry out. Now let's come one by one. We are going to find out what the simplification of the Boolean number. I think the simplification for Boolean number, you study it, I think, in second semester for year number 1 in logic. So we are going to summarize it, see how to simplify it. So this is S, okay? So this is S equal to this one. So this one, how you present it? We have this is 0, so this is will not count. So this is 1. It will be 1 when X invert or X dash, whatever you name it, but it's the name that the scientific name is X invert, because X 0, Y invert Cn. See here, X invert, Y invert Cn. One other point is 1 is here. So plus. So here x invert y cn invert. See here x invert y cn invert. Okay, there is more. Here is 0. We don't count this one. Plus this one. So this one, it's x y invert c invert. Because 0 0 y invert c invert. See here x y invert c invert. There is more. Here we don't count it because it's 0. Here we don't count it because we're 0. Here it will be count. So we have to put plus x y cn because all of them are 1. There is no invert here. X y cn. So that have been done for sum. Now let me simplify it. How we simplify it? We find out that we are going to take cn. Where cn is not invert. See here, this is cn not invert. Cn is 1. Where c invert is 1 is here. Sorry, it's here and here. So we are going to take cn as a factor, and then we are going to take cn as a factor. So this is cn and this is cn. Okay, so what's between two brackets? We are going to put x dash y dash or x invert y invert plus xy. See here, cn, we took this one and this one. Okay, because cn are factor. Okay, and we are going to take the Boolean part number, which is cn invert. So this is plus cn invert. We are going to take it. This is x invert y plus x y invert. See here, what is it? Sorry, this is x invert y. So cn. Okay, this is cn invert x invert y plus what is cn invert here? X y invert. So x y invert. Okay. After we simplify it, could we simplify it more? So we see here, it's possible to simplify it more. How? If we make all this invert, we are not making any change. We are going to make it same. So if I put invert to all of this, see here, this is bring it down and put invert to all of this. So this is cn. I am going to how to make this one invert. So this is to be x invert y plus x y invert. So that's how it will become. Now if you realize this is equivalent to XOR gate. So this is like cn XOR. If you look to the XOR table, this is equivalent to cn XOR x XOR y. So that's for the gates, to present the Boolean number for the gates for the summation. Now let's go for Cout. Cout, we are going to follow the same rule for what we did for summation. Now if you look to Cout, now here is 0. I'm not going to count out 0. I'm sorry, I have to go back. Here is 0. I'm not count out for 0. This is 0. Also don't care about 0. This is 0. Also I don't care about 0. Now here is 1. Here where Cout is 1. When is Cout is 1? Cout is 1 when x invert y cn. So look here, Cout. X invert, what is x invert? X invert y cn. So this is first one. There is more? Yes, there is more. Here is 0. We don't care about it. There is more here. So Cout is 1 when x y invert cn. Look here. So I have to put plus x y invert cn. Then there is more? Yes, there is more here. Plus, I have to put plus x y cn. X y cn invert here because it's 0. So here plus x y. So x y cn invert. See, cn invert. There is more? Yes, there is the last one, which is here should be x y cn. So plus x y cn. Okay. So that's how we translated from truth table to Boolean equation. Now we have to simplify the Boolean equation, same like the previous one. I am going to take Cn as a sharing part and Cn dash as a sharing part. So while Cn is sharing part, Cn is, mix. I'm going to take Cn. Okay, this is, I'm going to take x dash y plus what, xy dash. Okay, this is the one. Okay, there is a more Cn here. Here in this one here, if you realize that you could, there is a the variables or the bits for xy are same. So I'm going to take xy here. For this one, I'm going to take xy as a same number or as a same variable. So what's different here? Cn plus Cn complement or Cn invert. Now if you look here, x dash y or x invert y plus xy invert, this is like x XOR y, is same like this one here, x XOR y. See here, this is x XOR y. So I am going to take, this is Cn, okay, this is dot x XOR y plus, okay, so plus what, here is xy, okay, is xy, and Cn plus Cn dash, this is going to go. Yeah, why? Because Cn plus Cn dash what is 1. Some number, this is, from year 1. The number plus or the number the number or invert same number, that will be 1. So the number or invert same number or invert the same number, so that will be 1. That's rule, you know it in year 1. However, Cn or Cn dash is 1, so it's gone. This is will gone with this one. It's done. So this is, if you realize this one, so this is Cn XOR Cn dot x XOR y or xy, so this is to be C out. So that's the final. Now we are going to draw it on diagram. So how you draw the gates on diagram? Basically we do need x, y and Cn. Okay, now let's go for sum one by one. Sum, what is sum? Cn XOR x XOR y. So Cn, it will come on XOR gate, which is it will merge with x, and then it will go to the second XOR gate, merge with y to come C out. So you have 2 XOR gate. So Cn XOR gate with x, and the output, it will go to y, or sorry, x, the input x XOR gate with y, okay, both of them. So the results of these two, after it goes to XOR, it goes with XOR with Cn. So you have, this is XOR gate, and this XOR gate, the result of this one, it will goes XOR with Cn. If you look to sum now, x XOR with y, it will goes to XOR gate. So the result of this one, x XOR y, which is this one here, x XOR y. The result, the output of this result should goes to another XOR gate, and this is Cn. So this is x XOR y, so it will goes to XOR gate. It should be with another one, which is, if you follow here, which is Cn. Okay, Cn. So this is give you results of sum, x XOR y, it will goes to another XOR, and it will goes to Cn. That's that. This is the sum. Now what about the C out? Now C out, if you look here, the output of x or y, so I'm going to take the output of x or y, so same like here. See here, I'm going to take the same gate, I'm going to put it through AND gate with Cn. So first of all, I'm going to put it through AND gate with Cn, And the output of this one, I'm going to put it OR gate with X, Y. Now look here. So the output of X or Y, it will go to AND gate. AND gate with what? It will go AND gate with what? With, so the output of X or Y, it will go to AND gate with what? With Cn. So where is Cn here? Here is Cn. So the output from here, it will come AND gate with what? With Cn. So that's first one. This is Cn dot between two bracket X or Y. Okay. What else? I have to put it through OR gate. So I have to put the output of this one through OR gate with X and Y. Okay. So the output of this one, just I'm going to, what is the output of this one? The output of this one, so the output here, this is Cn X or Y. It will go to OR gate with what? With X and Y. Now if I look here, where is X and Y? So I have to put AND gate here. I am going to take X and Y. Okay, this is AND gate. So it will go where? To OR gate straight away. So the results of this one will be C out. So that's how we designed full adder and half adder. Now if you realize, just look to the diagram. This is XOR gate and this is AND. And this is XOR gate and this is AND. What you realize from this one, these two? You realize this is XOR gate and AND is similar to, like, if you look to the half adder, this is half adder, design half adder. XOR gate and AND gate. So that's the contents of half adder. So if you design full adder, you're required to design two half adder. Just mix two half adder, you will get at the final, as at the end, a full adder. So that's how you design a full adder. Next lecture, or tomorrow lecture, it will be 1 hour lecture. I am going to explain, to give you example for addition for 4 bits. So we are going to use 4 full adder. Just I'm going to give you idea about tomorrow lecture. So you are going to take 4 full adder. So here full adder 1, full adder 2, full adder 3. I am going to show you how to add 2 hexadecimal number. So this is hexadecimal number 1. Hexadecimal number 1 is 1011. Hexadecimal number 2 is 1110. How you are going to add these 2 hexadecimal number? We are going to find it out. That will be tomorrow. Of course, you will have, this is the full adder. What you have in full adder? You have a 3-bit. You have X, Y, and Cn. Here we have X and Y. This is represented as A and B. Cn is this one. Normally when you start the operation, any operation, so normally Cn is 0. Okay, Cn is 0. And you have, if you have a carry out left, this is C out. Okay, that's for full adder is very easy. For addition full adder, that's very easy. But when you are going to come to the subtraction, we have kind of controller called M. The controller must be 1, and I am going to explain tomorrow, inshallah. And if there is a carry out after the fourth bits of full adder addition, there is carry out, it means something. If there is no carry out, it means something else. So if there is carry out, that means the results is negative. If there is no carry out, that means the results is positive. I am going to explain it tomorrow. This is similar when we add the last lecture. You remember the last week lecture when we add the two binary numbers. So I told you when we did subtraction for 2 binary numbers. So we get the two's complement. So if the results there is a 1, that means we have to get the complement to the results in order to get the final results. So we are going to find it out tomorrow. That's for subtraction. Also, I'm going to go for overflow detection logic, and I'm going to explain for zero logic detection. That will be for tomorrow lecture. That's it for today lecture. I hope all of you enjoy it, having a good time. Thank you. See, talk with you for another topics tomorrow, inshallah. Bye.